This is part 2 of FAT32 analysis. Let us look at each field value and uncover its meaning. To avoid needing to translate value in little endian format, this table includes column hex value to translate the orders, the values. So the LSB, least significant bit, in this rightmost bit, field instruction offset hex value little endian EB. Okay, so we have here OME MS-DOS 5. This value indicates that the partition was formatted with the 2 using MS-DOS version 5. MS-DOS, the operating system, that provides a file system for operations such as reading, writing, and erasing on the disk. And it's not graphical line-oriented, command-driven computer system designed for the IBM PC. Several variations of DOS were developed, such as MS-DOS, Microsoft, and PC-DOS IBM. Bypass sector 1. Sector has size of 512 bytes. Structure per cluster. One cluster has one sector. This is often not the case. Cluster of 4 KB are used most of the time. Reverse sectors. Amount of the reverse sectors, including the boot sector, is 6270. After that, the FAT1 starts. Number of FAT. Okay, maximum root directory entries used. It's not used in a FAT32. Total sectors not available for FAT32. The original sector 32 value of the extend PB will be used. Media descriptor fixed disk sector base 4. This field is used for FAT16 and not for FAT32. This can be discarded. Sector per truck. A truck on the hard drive contains 255 sectors. This is a logical placeholder used for compatibility. It does not present real physical disk drive. Number of heads. The total heads of the drive is 255. 55. This value is logical placeholder used for compatibility. It does not present real physical disk heads. Hidden sectors. If we multiply this value with the sector size and convert it to GB to it becomes down to 49 GB, which is the size of the C partition. Total sector 32. If we multiply this value with the sector size and convert it to megabytes, it becomes down to 64 megabytes, which is the size of image. Sector per FAT. Amount of sectors assigned to FAT1 and FAT2, 2 times 960. Flux. This means FAT mirroring is enabled. FAT entries are simultaneously written to FAT1 and FAT2. Version. FAT32 version 0.0. Cluster root directory. Root directory is located at the second cluster of the data region. FS info sector. Information about the free clusters and next available cluster is located at sector 1, right behind the boot sector. Backup sector. Backup sector 6 contains the backup for boot information. Boot code contains the boot code necessary for BIOS or UEFI to boot up the volume. Unified Extendable Firmware Interface provides an interface between the operating system and platform firmware. Replaces the BIOS. BIOS, basic input and output system, is a boot firmware that provides runtime services for the operating system. The BIOS starts, checks specific hardware components and loads the OS depending on boot priority. FAT area. Very funny. FAT area contains a fail allocation table. FAT1 and FAT2 have the following functions. It contains information about the allocation of cluster to file, to directory and next free clusters. It helps with the fragmentation, data stored, and non-contiguous cluster files. It keeps tracks all the clusters that are assigned to the file. It does integrity check to identify bad clusters and mark them not to be used for storing data. Each entry of the file is 32 bits, but only 28 bits are effectively used. It is these 32 bits value that is referenced in a file system name FAT32. The file has to be interpreted together with the root directory entries for the files and directories. The root directory entries reference the cluster index number of the file where the file or directory starts. The index of the file entries corresponds with the index of the cluster in the data region. For example, hypothetical file A uses cluster index number 5 of the data area. Cluster index number starts at 2. Clusters 0 and 2 are reserved. The index number of corresponding file entry will be 5, counting from 0. Let us have a look at file 1 on our VM. Continue with the FAT32 structure. Let me real quick open this one structure. This is it. Image and navigate to offset 0, 3, 0. Nope. Let me see. You can calculate this offset value by taking value of this field multiplying by 512 bytes. Okay. Here we go. The offset, I hope this is it. Field size. Oh, yeah. Just made this one. So the back up of the FAT1, also named FAT2, start right after FAT1. To find the offset of FAT2, you need to add value of factors 961 field to the reserved 6270. Field, convert it to hexadecimal. Navigate to hexadecimal. This is it. So zeros, free cluster. This one, use cluster, next cluster in the chain XXX. Alright, back cluster. End of the foil and end of the foil. Okay. Use cluster. A cluster chain contains one or more clusters. Each entry in the data area has exactly one cluster chain style. The used cluster field the number of the next cluster that is a part of the chain. End of the file is to indicate the cluster that index is last cluster of the chain. Note the value 0f, and f are both used for making the end of the cluster chain. The difference lies in 4 bytes that are reserved. Some tools process this byte, others don't. The FF representation is simplified. Representations that did not take those 4 bytes into account. Generally, it's recommended by the standard to use the 0f version. Let's say we have file test text and its content is saved on a cluster 5 and 6 in the data area. Cluster 5 and 6 from a cluster chain. The file entry looks like this: used cluster, next cluster chain. This is the last cluster of the chain. Let's apply this knowledge to the entries of our file allocation table of the image on our view. Since FAT32 uses little endianness, we have to interpret each 4 bytes entry for right from right to left to get the correct value in the table below. Each 4 byte entry has already been reserved. So we got here end of the file. And so our first point of the point next BC. Let me jump to the questions. We have hypothetical B file. Its cluster starts at F and ends at cluster 10. What will be the value of the fair entry at the cluster F? Provide the value as you would read it in hex editor without spaces. Note B is not a file on the image. Let's go to hint. Remember the endian is very nice. So we can see here F8, FF0, F, FF, FF, FF. And here using the structure image, answer the following question. Which offset does at which offset does FAT32 table start? Given an offset value without space, remember FAT1 starts right after the reserve sectors and FAT2 start right after FAT1. Let me see. Index cluster for 1 and for 2. Let me see the hint. Formula reserve sectors. Sector per for multiplied by bar per sector convert to hex value. Reserved sectors per for. Reserved sectors. Reserved sectors. This is it. No way. Cannot be. Okay. For 1. Reserved factor. This is the best sector. Okay. For 30. Let me check this one. Show after some researchers get this page. The offset jump code, no, 3 bytes. 00H hexadecimal. I think this same table like we have in here looks like just maybe by default, something like that. Number of copies, maximum root, number of sets. I don't know. So now for the first question in task number 4. We have file B is cluster. Change starts at F. Ends at cluster 10. So starts at F, ends at cluster 10 of the new chain. Points to the next cluster. Starts at F and ends at cluster 10. This is it. And now reverse A into 10. Woohoo! So 10 We can see in here. Here. X, A, in X, A, 10. So it is 10 and all the zeros that we have in here. 4, 6, 8. That's it. This one is a bit trickier. This one we can find the start of the FAT table. Let me see. This is it. Reverse sector. Besides this wonderful table, we have start reverse sector, FAT table, data area, start with a cluster 2. Okay. So we have this one. Yep. 62, 17. Here's plus. This is reverse sector. Sector per FAT times 2. Let me see. Sector per FAT. Out of sector assigned to the FAT 1 and 2 times. This is it. 61 times 2. And all this times 5, 12. Let me see. Nope. So after some checking, I don't need these two, just this. So let me see. These two. Nope. 6, 2, 7 plus 6, 1. Wait, what? Six, 2, 17 plus 9, 6, 1. This is it. And now 512 D volt. Nope. No. And the do this in decimal plus 1 and now to hex. Multiply this one and now to hex. This is it. Maybe. Let me convert this one. We have, let me see. We're just meeting 3, 8. We have in here 6. Let me see. Let me see if 0, 0 in front of 3 will do the trick. Yes, that's it. That is it for this chapter. Just for to be clear in here, we do have to multiply it to 512. Let me demonstrate this one once again. Plus 9x1 multiply 5, 1, 2, and now convert this one to an hex. And we got 2 zeros in between. Because this is T volt. This is it. 40. 4 zeros, 4 zeros, 4 zeros, 4 zeros. This is 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8. Meaning every 4 zeros is a number, hexadecimal. That's it. So long for the next one.